Okay, so it's 970142 Feb March 2023. Okay, so part C, we have solved part B. Okay, I have uploaded the video. I would be sharing the link in the group. VO2 positive can be reduced to V2 plus by C2O42 minus in acidic conditions. Equation 2 says this in a titration 25 centimeter cube of 0.03 mole per dm cube VO2 plus is added to is added to 10 centimeter cube of dilute sulfuric acid. A solution of 0.04 mole per dm cube C2O42 minus is then added from a burette until the end point is reached. The titration is repeated and concordant result obtained as shown in figure. Table 3.1 show that these results are consistent with the stoichiometry of equation 2. Okay, of equation 2. So first of all, you would be solving, like you would be calculating the moles of VO2 plus. You would be calculating the moles of VO2 plus. Okay, and then you would be calculating the moles of C2O42 minus because the concentration and the volume is given to you. Okay, and then after finding out the moles of both species, then what I would be doing, I would be dividing it with the smaller number. So I would be getting the mole ratio. Okay. What they are saying, show that these results are consistent with the stoichiometry equation as shown in table 3.1. As shown in table 3.1. According to equation, the mole ratio between VO2 plus and 3 C2O42 minus is 2 is to 3. Okay, it's 2 is to 3. 2 is to 3 means that it's 1 is to 1.5. Of course, it's 1 is to 1.5. Okay, so after the calculation, we have to prove it. So what I did, I have calculated the moles of the both species. Okay, then what I saw, I looked at the smaller value. The smaller value is 7.5 exponent minus 4. Then I have calculated both values by the smaller number. Like we do the same thing in finding out the empirical formula, if you remember this. Then I got the mole ratio, that is 1 is to 1.5. That is, of course, 2 is to 3. Okay. So this is of 2 marks. Then in part 2, they are saying an excess of C2O42 minus reacts with VO2 plus to form mixture of two octahedral complex ions. Octa means when the coordination number is 6. The complex ions are stereoisomers of each other. Each complex ion contains a V2 plus cation and 3C2O42 minus ion. Okay, 3C2O42 minus ion. Okay, complete the diagram to show the three-dimensional structure of one of the complex ions. Include the charge of the complex ion. As you can see, this OO is a bidentate ligand. Each bidentate ligand is going to donate two lone pairs of electrons and it's going to make two dative bonds. So if you have three C2O42 minus ion, that is the three ligands, so it would be making overall six dative bonds. Of course, the coordination number would be six. That's the reason it's octahedral complex. It's what? It's octahedral complex. Okay. So let me tell you this. Okay, octahedral means that when the coordination number is 6. So if you have three bidentate ligands, if you have three bidentate ligands, they would be making 6 dative bonds. And if you can ask the definition of coordination number, so I would be telling you that the number of dative bonds between the metal and the ligand, the number of dative bonds between the metal and the ligand. Okay. And also they are asking the charge, include the charge. What's the charge on vanadium? You know, the charge on vanadium is 2 plus, they have mentioned. So if you have one vanadium and you have three ligands, each ligand is going to have -2 charge. Okay, so that would be +2 and -6. Of course, that would be -4 in total. That's the reason I have written -4. Then part D says V2 plus can be oxidized by hydrogen peroxide, that is H2O2. Table 3.2 gives some relevant data. Okay, 1.771, 0.34 minus 0.26. Identify the vanadium species that forms when an excess of H2O2 excess means reaction would continue. Like it would be reacting continuously. Like if you remember in organic chemistry, we used to discuss if you are going to oxidize primary alcohol, so it would be oxidized into aldehyde first, and continuing the reaction, it would be further oxidized into the carboxylic acid. It's a continuous reaction. But in that case, if you have a excess of like you are going to have a heat under reflux, you are going to do continuous chemical reaction. Okay, same goes over there. They are saying we have excess of hydrogen peroxide, so of course the reaction would continue and it would be oxidizing multiple times under standard conditions. Explain your answer with reference to the data in table 3.2. So, okay, vanadium is 2 plus. Vanadium is 2 plus. When it would be oxidized, it means that oxidized. Like, let me tell you this. Okay, if vanadium can be oxidized, so means that it's a loss of electron. It's a loss of electron. Okay, so of course V2 plus after oxidation, it would be forming V3 plus according to this equation. Am I right? According to this equation. Okay, according to this equation. So then, of course, they are saying excess of hydrogen peroxide. So continuously, then it would be oxidizing into this, and then it would be oxidizing into. So your final product would be VO2 plus 1 ka charge. Okay, identify the vanadium species. I would say that is this. This is your final species. Why? Because they are saying excess of hydrogen peroxide. What they are saying? Excess of hydrogen peroxide. That's the reason. So, excess of hydrogen peroxide would be continuing the reaction, and finally, you would be getting that species. So, I have written VO2 plus will form as E naught of H2O2 is most positive. Of course, if it is more positive, if the E naught value is more positive, it's a strong oxidizing agent, and E naught value of VO2 plus is the less positive value. Okay, it's the less positive value than H2O2. H2O2. Okay, so it's of 1 mark. So I have written the continuous reaction. First of all, V2 plus 2, 3 plus, then 3 plus 2, VO2 plus, that is this. And then VO2 plus 2, VO2 plus, that is this. Finally, concentrated hydrogen peroxide can react with V2 plus to form red VO2 3 plus ions. VO2 3 plus ions contains vanadium combined with the peroxide anion. In the peroxide anion, O2 2 minus, in this oxygen is -1 because this is peroxide. The general oxidation number for the oxygen is -2. You know very well. Okay, it's a common concept that oxygen is -2. But in peroxide, oxygen is -1. So I'm going to have -1 over there. I'm going to put -1 over there. Then I would be getting the charge of vanadium that is +5. So that's the reason the answer is +5. Okay. Then question number 4 says ethylamine and phenylamine are primary amines. These two compounds are synthesized by different methods. Several methods can be used to form ethylamine. Ethylamine forms when ethanamide is reduced by LiLH4. That is a stronger reducing agent. Okay, this is your amide. Write an equation for this reaction. Use H to represent one atom of hydrogen from the reducing agent. Basically, this is the symbol for the reducing agent. So when you are going to reduce this amide, okay, ethylamine would be formed. Ethylamine is this. This is the formula for ethylamine. This is the formula for ethylamine, and like rest of the product would be water. That's it. Okay, so 1 mark only. Ethylamine is a product of the reaction of bromoethane with ammonia. It's a nucleophilic substitution reaction where the bromine would be replaced by this ammonia. Okay, would be replaced by this, like you can say ammonia. Name the mechanism of this reaction and the state of the conditions used. This is nucleophilic substitution reaction. Condition ammonia in ethanol. Why not ammonia aqueous? If you are going to have ammonia aqueous, so rather than ammonia, the OH would be substituted and alcohol would be formed. That's the reason we have taken ammonia in ethanol. Okay, it can be concentrated ammonia as well. Okay, this the reaction in A part two. The reaction in A part two. Okay, also forms secondary and tertiary amines. So just the identity of a secondary or tertiary amine formed by the reaction in A part two. Okay, so this is your secondary amine. This is your secondary amine in which you can see two R groups with this nitrogen atom and one hydrogen atom. So it shows that this is your secondary amine. Okay, because in reaction in A part 2, primary amine is formed. Primary amine is formed. Okay, so they are saying the reaction in A part 2 also forms secondary and tertiary amines. How? Let's suppose if you have this, okay, the ammonia would be attacking on this CH2 that is positive. Okay, why? Because Br is negative. Br is negative. So it's called um, you can say positive inductive effect. This is an electron donating group. It's going to donate electron to this bromine. So that's the reason it's a positive charge over there. Then ammonia is going to attack on this positive carbon. Okay, it's going to make bond. Okay, then this is the leaving group. And finally, you can see, okay, this is produced. Okay, finally, you can see that this is produced. Same goes with, say, you can form the secondary amine as well, and you can form the tertiary amine as well. Okay, so this is your secondary amine. They were saying secondary or tertiary. So I have written secondary. You can also write down the tertiary amine, okay? Then part B says ethylamine is a weak base. Say the relative basicities of ammonia, ethylamine, and phenylamine. Explain your answer. Basicities like ability to become a base, ability to gain proton, ability to accept proton. If the base is going to accept proton more easily, it's called a strong base. And if the base is not going to gain proton easily, so I can say that this is a weak base. This is a weak base. Okay, so what about phenylamine? So structure for ammonia is NH3. It's ethylamine and it's phenylamine. Let me tell you something important, okay? That this lone pair isn't available. If you ask why, because this lone pair is delocalized into the ring. Because the nature of the ring is electron withdrawing. It can catch electron. It can accept electron. Okay, so these lone pairs are delocalized into the ring. So it would be not available to the coming acid. It would not be acting as a base. So let's say if in case it is a base, so it is a very weak base. You know why? Because it's not going to give its proton easily. Or in other words, I can say it's not going to gain proton very easily. Okay. It's not a good lone pair. It's not a good proton acceptor. That's why it's a weak base. And if you can talk about this, in this you can see that this is R group, and R group is an electron donating group. When electron donating group is going to donate their lone pairs, so of course already the one lone pair is available, so the repulsion is going to take place. As a result of this lone pair is more available. When it is more available, so it can accept proton easily. It's the strongest base, and ammonia is lying in between the phenylamine and ethylamine. That's the reason the least basic one is phenylamine. Why? And the most basic one is ethylamine, because ethylamine is most basic due to the ethyl group, which is an electron donating group, which increases electron density on nitrogen. Of course, when the electron density would be increasing, so what is the proton seeking? What is proton seeking for? Any negative area. Of course, it has a positive charge. When it would see the negative area over the nitrogen which is present in the ethylamine, So it can accept proton easily. Phenylamine is least basic. Why? As p orbital of nitrogen overlaps with pi electrons of the ring, which allows lone pair to delocalized into the ring. So phenylamine cannot gain proton easily. That's the reason. This is of 4 marks. This is of 4 marks. Okay, it's very easy. Then in C, pure phenylamine can be prepared from benzene in 2 steps. Draw the structure of the intermediate compound, suggest reagents and conditions for each step. So they are saying we have to form phenylamine from benzene. Benzene is the starting material. Of course, benzene is C6H6. You know, you cannot attach NH2 directly. You cannot attach NH2 directly. Why? There is no such reagent. By using that reagent, you can attach NH2 over the benzene ring. So, of course, it's my compulsion. I have to form this first. This is called the nitrobenzene. So, you must know the reagents and conditions for the nitrobenzene. So if you are going to react this benzene with the concentrated sulfuric acid and concentrated nitric acid, and you are going to provide this much temperature to this benzene, so then the nitrobenzene would be produced. And then after the reduction with this 10 plus HCl concentrated, then it would be reducing into this NH2. It's called phenylamine. Okay. So you have produced the phenylamine in 2 steps. First of all, you have formed nitrobenzene and then you have formed like the phenylamine. Okay, it's also known as aminobenzene. Then part D says figure 4.2 shows some reactions of phenylamine. Okay, uh, then they are saying part one, draw the structure of W, the organic product of reaction one. So phenylamine in this NH2 has a lone pair of electron. Now you have to see what is the nature of this NH2 group. Of course, this is an electron donating group. So what the electron donating group does, of course, it's going to donate its electron to that benzene ring and it increases the electron density on the nitrogen of the benzene ring. So also it's a 2,4,6 director. Like already when the NH2 is attached to the benzene ring, so when you are going to react that benzene ring with any of the electrophiles, so the NH2 would direct the coming electrophile to 2,4,6 positions. So so that's the reason the Br would be attached on the 2,4,6 positions. If this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, so that's the reason what I did. I have attached the bromine atom on 2, comma 4, comma 6 position. 2, comma 4, comma 6 position. Okay, that's why. State the reagents used in reaction 2. In reaction 2, if you can see, this is going to change into this. Of course, this is N triple bond N. Okay, I told you when we were discussing organic nitrogen compound, it's a topic of diazonium salt in which we have formed the azodia that was of the yellow color, if you remember. If you remember, okay. So, so of course we did react with this NaNO2 that is called sodium nitrite with HCl. NaNO2 plus HCl. Whenever you are going to react NH2 with this, you can say NaNO2 and HCl. Okay, so it would be forming the diazonium salt. The diazonium salt. Okay, then benzene diazonium chloride and X. Benzene diazonium chloride and X. Okay, mm, react together in reaction 4 to form Y. An azodi, an azo compound. Hmm? Hmm? Y is an azo compound. Okay. Azo bole to nitrogen. Okay. Name X, the organic product of reaction 3. So first of all, you have to convert this into phenol. That is this. Okay. Then it they would be reacting with each other to form this Y. Okay. They would be reacting with each other to form Y. So that's the reason I have written this is phenol. Okay. Then state the necessary conditions for reaction 4 to occur, of course, sodium hydroxide, because we have to add sodium hydroxide in it. You know why? You know, phenol has acidic nature. It would be forming this compound. Then it would be reacting with this to form this compound. Okay. Suggest a use for Y. Of course, this is a dye. It's a coloring agent. It's a dye. It's a colored. In textile industry, we can use this. Okay. Part E says methylamine is another primary amine, can act as a monodentate ligand. Define monodentate ligand. So monodentate ligand, which can donate one lone pair of electron, which can donate one lone pair of electron, and of course, it's going to make one dative bond with the metal cation. Okay, or you can say a single covalent bond. Hmm? Hmm? Copper 2 plus react with methylamine to form this complex, okay, where the coordination number is 6. 4 water and 2 methylamine, where the coordination number is 6. Okay, so they are saying draw three-dimensional diagrams to show the two geometrical isomers of this. So what I did, okay, geometrical isomers they are going to ask. So this is trans, this is cis. Why this is cis? Because the bond angle is 90 degrees between the two same ligands. And why this is trans? Because the bond angle is 180 degrees between the two same ligands. That's why this is the trans. So this is cis and this is trans. So these are the two geometrical isomers. Okay, these are two geometrical isomers. Okay, it's very easy. Then state the coordination number of copper in copper CH3NH2 water. So you know the charge of this is -2. Okay, so -2 and then this is 0. Of course, the charge on copper would be, you can say, if this is -2, so you can say that 2 into 2 is 4 because you have two ligands. 2 into 2 is 4. Okay, or this would be +6. Okay, this would be +6. And then they are saying uh, cadmium 2 plus ions form tetrahedral complexes with CH3NH2. Okay, OH minus and Cl minus ions. Okay, as shown in equilibrium 1, 2, 3. Give the units for K stab for equilibrium 1. Can you solve it? Are you getting the same unit as I did? Are you getting the same thing?
Yes, sir.
Okay. Then write an expression for K stab for equilibrium 3. Okay, product upon reactant. The formula is same. That is product upon reactant. Okay. And part 3 says a solution of Cl minus is added to cadmium 2 plus and allowed to reach equilibrium. The equilibrium concentrations are given. Cadmium is this and Cl minus is this. Okay. So they are saying use your expression in F part 2 to calculate the concentration of cadmium chloride in this equilibrium mixture. Okay, where the Kc is given to you, that is 6.3 exponent 2. Okay, they're talking about that equation, equilibrium 3. Okay, so I have used the same thing. They have given the concentrations of cadmium and also the chloride ion. Of course, I would be finding out the concentration of this. I would be multiplying this and then I would be multiplying with the Kc value. So I would be finding out the concentration of this CdCl4 2 minus. this CdCl4 2 minus. Okay, it's very easy. It's very easy. Okay, or okay. When CH3NH2 is added to cadmium 2 plus, okay, a mixture of this and also formed. Suggest how the CdOH4 2 minus is formed. Uh, Basically, they are talking about when CH3NH2 is added to CD2 plus. Okay, CD2 plus. So this is going to form. Okay, they are saying a mixture of this and this is going to form. They are saying suggest how CdOH4 2 minus is formed. How CdOH4 minus is formed. So you will say, okay, this is basic in nature. Why? It's going to have a lone pair of electron. It reacts with water. It reacts with water. Okay. To produce OH minus ion. To produce OH minus ion. How? Let me tell you this. Let me explain it. Okay, this is CH3NH2. It's water. That would become this, and it's releasing OH negative ions, and then that's the reason cadmium hydroxide is formed. That's the reason cadmium hydroxide is formed. Okay, very easy. Uh, Cadmium 2 plus exists as a complex ion. Identify the most stable and the least stable of the complexes in table 4.1 by placing one tick in each column. Hmm? What is the most stable one? If you can see the higher K stab value, if you can see the higher K stab value, so I would say the complex is more stable. And if you can see the lowest K stab value, if you can see the lowest K stab value, so you can say the complex is least stable one. The complex is the least stable one. Okay. So I have seen that this is going to have, this is going to have, okay, no, this is going to have the higher value, I think. Am I right? Hmm? Highest 10 raised to the power 8. So I can say that this compound is the most stable one because it has the highest K stab value, of course. And then what's the least stable? What's the least stable? Okay. So the least stable one is, I think so, you can say cadmium water. So cadmium water is what? It's the complex at the normal conditions because mm, when you have CdH2O6, it's a normal complex ion. Okay, so it would be the least stable one. That's the reason it's going to react with the ligands. If this would be more stable, so there is no reason to react with someone else. So okay. So explanation case tab of CdOH42 minus has highest value. Now they are saying contains a benzene ring. Tolubutrol contains a benzene ring in its structure. Describe and explain the shape of benzene. Of course, benzene is going to have the double covalent bond, the carbon-carbon double bond. Okay, carbon-carbon double bond means that they are going to have alternative positions. Okay, electrons are delocalized. Okay, electrons are delocalized, and then each carbon is going to have sp2 hybridization. Each carbon is going to have sp2 hybridization, and the sigma and also the pi bonds are going to form. Sigma and pi bonds are going to form. Okay, and what I did, all carbons in benzene are sp2 hybridized and having trigonal planar shape. Overall shape of benzene is hexagonal planar and bond angle is 120 degrees. Pi bond is formed between the sideways overlapping of the p orbitals from each carbon atom. Like sideways overlapping means that the p orbitals are going to overlap in this manner. Since the overlapping area is minimum, so this can be broken down very easily. That's why it's a pi bond. Pi bonds are weak bonds. But if you are talking about the head-on overlapping, so it's called head-on overlapping. The like the overlapping area of the head-on overlapping is maximum. That's the reason it's a stronger bond. More energy is required to break down that bond. That's called, this is the pi bond. This is a sigma bond. Okay. Then part B says, write an equation to show how the chlorine reacts with AlCl3 to generate an electrophile. Of course, it would be reacting with this AlCl3, which is used as a catalyst. It would be forming electrophile, that is Cl plus, and rest of the product would be this. Then draw the structure of the intermediate. Of course, it's very common. I'm not supposed to tell you this. Whatever the electrophile you have, you would be doing the same thing. You would be doing the same thing because let's suppose this is Cl plus. Of course, the pi electrons are going to attack on this and it would be forming an intermediate. Of course, you have broken down the stability of that benzene ring. All the carbons were delocalized. That was more stable. But of course, right now only the 5 carbons are having delocalized electron. One carbon is the single one, which is going to make this benzene less stable. To gain its stability, hydrogen would be donating electrons to recover the stability of the benzene ring, and it would be removed from the ring in the form of H positive ion that would be reacting with this AlCl4 minus to form again AlCl3. That's the reason we can say LCl3 is used as a catalyst, because the AlCl3 is regenerated in the end of the reaction. That's the reason. That's one of the reason. Okay. Um, then name the mechanism. Of course, it's electrophilic. Benzene most of the time, 100, like 99.99 times, it's going to give you electrophilic substitution reaction. Draw the structure of an isomer of Q that forms as an organic byproduct of the reaction in step 2. Step 2, step 2, step 2, step 2, step 2, step 2, step 2. This is your Q. They're asking an isomer of Q. What I did, I have changed the position of carbonyl group. That is this. Oh, this is an isomer. Okay, molecular formula is same. The structure is different. It's called functional group isomer. I have totally changed the functional group. It was ketone. It's an amide. It's called functional group isomerism. So it was a ketone. Okay, that's it. Mhm. The reactants is used in step 2 contains acyl chloride, alkyl chloride, and aryl chloride functional group. State and explain the relative ease of hydrolysis. Okay, of acyl chloride, alkyl chloride, and aryl chloride. Um, Hydrolysis, it's going to react with water, okay? So we have to see how much the CCl bond is stronger. If the CCl bond is stronger, it would not be hydrolyzing easily, okay? Then the more energy would be required, of course. Okay, so easiest to hydrolyze is acyl chloride. Let me tell you, acyl chloride is this. This bond is weaker as compared to aryl chloride. Aryl chloride is this. It's an electron donating group. So it's going to donate its electron to the benzene ring. It's going to make a double covalent bond with that benzene, which makes it stronger. It's not going to break down easily. That's the reason. It cannot be hydrolyzed very easily. Hydrolysis means that the chlorine containing product would be reacting with water to form an alcohol. It's in an easier manner. Okay. Okay. So okay, what I said, CCl bond in acyl chloride is weaker as carbon is more electron deficient. You know why? See this? These two are electron donating electronegative atoms. They are going to pull electrons towards itself, makes this carbon most positive, of course. So it's an electron deficient due to the presence of chlorine and oxygen, which are highly electronegative. In aryl chloride, the CCl bond is stronger. So of course they are going to make this bond weakest. And in aryl chloride, The bond is double bonded, as I told you. So the it becomes more stronger. It's not going to break down easily. That's the reason. Hardest to hydrolyze it's aryl chloride, and easiest to hydrolyze is acyl chloride. Okay. Then suggest reagents and conditions for step 3 and 4. So if you can see Z, now you can see this. It's going to attach and is an extra. This is ketone. Okay, it's an alcohol. So what I did, first of all, I have reacted in step 3 this in ethanol so that chlorine can be replaced by that group. It is carbon CH3, then CH3, then CH3. So CH3 thrice, CH3 thrice, which is attached to that carbon, which is attached to this CH2 NH, CHNH2 in ethanol. Make sure you are not supposed to take it in the form of aqueous, because when you would be taking in the form of aqueous, so the OH would be substituted by this chlorine, of course. So to prevent this reaction, because they have given us the product, so make sure you have to form this product by any means. And in step 4, I have reduced that into the alcohol. That's it. Simple, very simple. Okay. Then they are asking Z. That would be the Z. It is having ketone in the next step. Step 4, we have converted this ketone into alcohol. Okay. Mhm. So, um, rest of the paper you are supposed